If you've ever been in an elevator ride, you definitely would have felt this. While the elevator is ascending, you suddenly feel quite a bit heavier. And if you're at the top of the building and the elevator starts descending downwards, you suddenly feel quite a bit lighter. Now, are you really gaining extra weight or losing weight while you're in an elevator? As in physically adding mass or removing mass? Well, that's not the case, all right? But you are feeling this weird illusion that you're suddenly feeling heavier or lighter. And this illusion is known as apparent weight. Apparent weight only happens in a non-inertial frame of reference. In other words, you're accelerating, and then you suddenly feel all these additional forces acting on you. That's really throwing you off from your game. What you're really feeling when you're in an elevator is the normal force of the ground acting on you. So before we get into any more detail with regards to apparent weight, let's talk about your weight when you're at rest, or if the elevator is in constant motion. Because interestingly enough, while the elevator is ascending or descending, you won't notice anything other than your ears popping if you've ever been on the CN Tower before. All right, so let's just start off with our weight that we experience while the elevator is stationary or while it's moving constantly up or down. So you as an object, let's just make you a whole lot lighter, having a mass of 1 kilogram. What are the forces acting on you when the elevator is stationary? Correct, there's just two. Not only is the gravity acting on you with the force of gravity pointing downwards, the surface or the ground of the elevator is holding you up, the normal force, and that's it. And if the elevator is stationary or moving at constant velocity, you know that your F net will go to 0. So the normal force subtract the force of gravity will equal 0, and that's why the normal force is the weight that your feet feel. In this case over here, with a 1 kilogram apple, it feels a weight of 9.8 newtons. We're going to keep that number down here as a reference value. Let's say you're at the top of a skyrise, and the elevator begins to accelerate downwards, quite fast. You should feel quite a bit lighter, so your value for your normal force should drop. Let's see if that's true in our calculations. First thing we should always do in a force problem is to draw a free body diagram. That's correct. Force of gravity is acting downwards on you, but luckily the floor of the elevator is holding you up, and that's what you're sensing as your weight, the normal force. F net is equal to Fn minus Fg. But F net is also equal to ma. Therefore, ma is equal to Fn minus Fg. You'll be bringing this term over here and then subbing in as necessary. Just be careful in your substitutions. Even though your acceleration will be negative, you might be wondering, should I be placing my g as negative or not? And the answer is no. You should be keeping your g as positive 9.81. And if you're wondering why, it's because look what you did before. You've already assumed that gravity is pulling you downwards. Remember that in your original F net expression, you assumed Fn was positive and Fg as negative. And as such, there's no point putting another minus sign for 9.81. So calculate through that, and you'll notice that you end up getting an answer that should be less than 9.81. Awesome. All right, now you're at the ground floor and you want to start all over again. But this time around, the elevator struggles as it accelerates upwards. So the upward acceleration isn't as great as its downward acceleration. But you should still feel heavier. So go ahead and go through that math. Hopefully that gives you enough time to work through it on your own. In this free body diagram, your acceleration will be upwards. Okay, so you have a positive 3 meters per second squared. In fact, the formula will look exactly the same as before. There won't be any difference. The only difference now is that you're subbing in plus 3 into this term over here. And as a result, your normal force should increase. Once again, this change in your weight comes from a different frame of reference, known as a non-inertial frame of reference, or an accelerated frame of reference, where these additional fictitious forces start acting on you, throwing you off from how you should naturally feel. For more adventures like this, get started on your homework. And if you're stuck with it, follow along with me now. Okay, so you're standing on a bathroom scale in an elevator, and the normal force acting on you would be the reading of the bathroom scale. This number is called your apparent weight. For the following cases, use a free body diagram and an F-net statement to calculate the following. First off, when the elevator is at rest. Once again, if the elevator is at rest, this term goes to 0, so then your Fn is equal to your mg. So 70 kilograms times 9.81 newtons per kilogram will give you 687 newtons. Now, the elevator is moving upwards at a constant speed. Remember, at a constant speed, acceleration is equal to 0 meters per second squared. And if acceleration is equal to 0 meters per second squared, then if F net is equal to ma, F net also goes to 0. Therefore, answers A and B will be the same. It'll still be at 687 newtons. Next, the elevator is moving downwards with an acceleration of 2 meters per second squared. So if you assume upwards is positive, then your acceleration here will be at negative 2.00 meters per second squared when you sub it into this formula. You probably want to isolate for Fn, so you bring this term over here, and you get Fn is equal to ma plus mg. And then when you sub in your a over here, it'll be negative. Don't forget that your g will be positive 9.81, as you've already factored in the minus sign in the statement before. It's just in the rearranging, the minus sign disappears. That's all. All right. So if you're moving downwards, then your weight should be less than before. So it won't be 687 anymore. Now your Fn will be at 547 newtons when you calculate it through. And lastly, when you're free falling, how do you deal with that? Well, as you're free falling, you know that your acceleration is matched with the force of gravity at 9.81 meters per second squared. That's why when you sub it in here with a minus 9.81 and here with a positive 9.81, and the masses being exactly the same, your Fn will work out to, that's correct, 0. You'll feel weightless while you're free falling. Something that Einstein noticed and made him start thinking about relativity. It's pretty crazy. Okay, number 8. An elevator and its load have a combined mass of 800 kilograms. The elevator is initially moving downwards at 10 meters per second and slows to a stop after 25 meters. What is the tension experienced on the rope during this rate of deceleration? Okay, so we got to sit down and figure that out. We know that our F net, which is equal to ma, is equal to tension minus mg. Now, to solve for the rest of this, we got to solve for acceleration first. So how about we go through that on the side, our kinematics. All right, we have a VI of initially, sure, we'll do with everything assuming upwards is positive. So you're moving downwards at negative 10.0 meters per second. Your VF is equal to 0 meters per second. And your delta D is that it's going downwards of negative 25 meters. What is your rate of acceleration? All right, so you'll be using the formula VF squared is equal to VI squared plus 2A delta D. When you isolate for A, you get VF squared minus VI squared all over 2 delta D. Right. That's my bad. Yeah, acceleration will be equal to plus 2 meters per second squared, meaning that acceleration will be in the opposite direction. That will be the case, right? As we're going down and we're slowing down, our acceleration is upwards. That is true. Okay, so the tension on a rope should increase. It's the same thing as if you're accelerating upwards. So as you're decelerating downwards, it's the same as accelerating upwards. The tension would increase. So what exactly is that tension? That's equal to ma plus mg. We could factor out the m if you want to, a plus g, just to make life easier. So 800 kilograms times an acceleration of 2.0 meters per second squared plus 9.81 meters per second squared is the same as, where's our calculator? 800 times 11.81, which will give us 9,448 newtons. And I hope that the rope on the elevator can handle that kind of tension. What would be the apparent weight of a 50 kilogram person in this situation over here? Well, in this case over there, there'll be ma is equal to Fn minus mg. Okay, so our Fn is equal to m a plus g. So for the 50 kilogram person, well, for one thing, let's just take a look at the reference value. Okay, if they were stationary in the elevator, then they should have a value of 50 kilograms times 9.81, which is roughly around 500 newtons. So in this case over here, we should have more than 500 newtons in our solution. More than 500. Now we have 591 newtons. And C, what would the apparent weight of the 50 kilogram person be if the elevator was initially moving upwards at 10 meters per second squared before coming to a stop on a 25 on a floor 25 meters above? Well, in this case over here, our VI would have been positive 10 meters per second, and our D would have went upwards 25 meters. So there's a plus sign inside here, and this positive sign over here. Well, negative divided by positive will give you a negative. So if you're going upwards and you're slowing down, then you're decelerating upwards. In that case over here, you'll have an A, which is at negative 2 meters per second squared times 9.81. So when you pull on your calculator, it's going to be at 7.81, which would give you a weight of 391 newtons. Now, you should feel lighter at that moment, and that's how you'd solve number 8.